Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of InnoEnergy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the fourth one. This lesson is divided into several parts. Let's begin by studying the equations that govern heat transfer through composite cylindrical walls. For the calculation of the insulation of pipes, we must apply the knowledge of calculation of cylindrical composite walls. The thermal resistances are similar to those of the plane wall. However, they depend on the radius. And the outer surface depends on the thickness of insulation. Because the outer surface depends on the insulator thickness, it is needed to solve the system of two equations for all cases. Let's find out what a critical radius means in the insulation of a cylindrical wall. In pipe insulations, when increasing the insulation thickness, the outer surface increases, making the surface exposed to convection and radiation larger. When insulating a pipe, like in plane walls, the outer surface temperature always decreases when increasing the insulator thickness. When plotting heat losses as a function of the insulation thickness, it can be seen that losses increase for the first millimeters. After a maximum, losses decrease. The radius for the maximum of heat losses is called the critical radius. You can use the heat balance in the outer surface of the insulator for a given value of thickness. Using the heat balance equation, you can find the outer surface temperature. Using this temperature, you can calculate the heat transfer rate per unit length of pipe. In this way, you can plot a curve and approximate the value of the critical radius, calculating losses for different values of the thickness. If radiation with surroundings is neglected, the thermal circuit is formed by four thermal resistances that do not depend on the outer surface temperature. When compared with the thermal resistance of the insulator, the thermal resistances of the internal convection and pipe wall can be neglected. For the maximum of heat losses, the thermal resistance must show a minimum. Calculating this derivative, we arrive for a very simple expression of the critical radius as a function of the thermal conductivity of the insulator and the outer convection coefficient. Finally, let's apply these equations for calculating the insulation of a pipe. Peter is working as engineer in a factory. His manager is very angry because the energy bill is too high and asks Peter to do something to reduce it. Peter identifies which pipes are critical and decides to replace the old insulations by new ones of lower thermal conductivity and higher thickness. Can you help Peter to design the insulation for one of the critical pipes? Remember that for the calculation of composite cylindrical walls, it is needed to know a set of data, which include dimensions, properties, and boundary conditions. Recall that making the energy balance in the outer surface, we can first calculate the outer surface temperature. This temperature is very close to the maximum allowable temperature for safety reasons in industrial facilities. This is clearly an energy expense we can reduce significantly. After talking with Peter, we had agreed to plot the heat losses against the new insulation thickness. We use the same data except the thermal conductivity of the insulator and its emissivity. For each value of the thickness, we must first calculate the surface temperature. Moreover, after that, the heat losses for this pipe with the new insulating material.
After plotting the results, I suggest you to install an insulation between 50 and 80 millimeters. Higher values of the insulator thickness do not increase significantly energy savings.
After consulting catalogs, Peter has found that for pipes of outer diameter of 25 mm, there are standardized pre-slit insulations of 50 mm thickness that are cheap and easy to install. For an insulation of 50 mm, the outer surface temperature decreases to near 32 Celsius degrees. Losses for this 25 m long pipe are reduced to around 300 watts. Taking into account that this equipment works 7,000 hours per year, saving are around 6,177 kilowatts-hour per year. Assuming a tariff for your company of 4 cents per kilowatt-hour, for this pipe you save around 247 euros per year.
For this 25 meters pipe, I've received a quotation of 500 euros for materials and labor hours, all included. Therefore, the TIR is around 2 years.
After calculating savings for all the critical pipes in the factory, Peter's boss can feel very happy about the increase of energy efficiency proposed for the company.